Good morning to all. I am from BSc Chemistry Honours second year. Today we will discuss the chapter of Inorganic Chemistry and the chapter name is Chemistry of Actinides. So let's start the chapter. Actinides constitute a series of elements following actinium in the seventh period of the periodic table. Actinides belong to F block as these are formed by the gradual filling of 5F subshell. We have discussed the chemistry of lanthanides in the previous chapter. Lanthanides which follow lanthanum involve the gradual filling of 4F subshell. In this chapter, we will discuss the chemistry of another series of 14 elements which follow actinium. This series of 14 elements is called the actinides. Actinides along with lanthanides constitute complete F block elements. The ending is IDE in actinides is not because it more correctly negative ion such as oxide or chloride. Actinides were also named actinons by a group of scientists. However, the ending "on" is used preferably for non-metals such as boron, silicon, etc., whereas all the actinides are distinctly metallic. IUPAC name has now recommended these elements to be called actinoids with the ending "oid" rather than being called actinides or actinins. However, it is unfortunate that people still call these elements by their earlier name as actinides. Before World War II, the only naturally occurring actinides, namely thorium, protactinium, and uranium, were known. Uranium is the heaviest naturally occurring element. It was after World War II that the remaining elements were artificially discovered through nuclear reactions. These elements are named man-made or synthetic elements. Another name coined for these elements is transuranic elements. Transuranic elements are the elements that have atomic number greater than 92. Let us know discuss the interesting aspects of the chemistry of actinides. So the first point is position of actinides in the periodic table. An inspection of the periodic table reveals the electronic configuration of noble gas radon as 54 xenon 6s2 4f14 5d10 6p6. After radon, the 7s and 7p orbitals gain stability relative to 5f orbital because s and p orbitals are more penetrating than the d and f orbital. As a result, the next two electrons are being filled in the 7s orbital, which mark the appearance of new elements francium and radium belonging to S block of elements. After the addition of two electrons in the radon core, the 5f and 6d electrons penetrate the 7s orbital. The least penetrating f orbitals are stabilized on account of the increase in effective nuclear charge outside the next noble gas core with increasing atomic number. As a result, the next 14 electrons from thorium to lawrencium enter the 5f subshell. It is important to note that around actinium, both the 5f and 6d subshell possess almost similar energies. Because of similar energies of 5f and 6d subshells, the incoming electron may enter either of the two subshells, which results in the uncertainties of the electronic configuration. As a result, it is doubtful whether the electron enters the 5f orbital or not. However, once filling starts in f orbital, the 5f subshell becomes more and more stable. As a result, from uranium onward, the 5f subshell becomes most stable. Thus, all the incoming electrons starts filling progressively in f orbitals. The general electronic configuration of actinides can be as signed: radon 5f0 14 6d0 to 1 7s2. Then we can see the graph which is between binding energy and atomic number of actinides. And the second point is general characteristics of actinides. Some of the general characteristics of actinides are detailed as electronic configuration. As we have already discussed in section 5.1, the actinides involve the gradual filling of 5f subshell. The electronic configuration of the titled actinium is radon 6d1 7s2. Thus, from thorium onward, the 5f subshell starts progressively filled. The general electronic configuration of the atoms of actinides in the ground state may be written as radon 5f 1 to 14, 6d0 to 1, 7s2. The detailed electronic configuration of all the elements we can see in the table. Let's have a look on the table of actinides. So the second point is physical properties. Some of the physical properties of the actinides are presented in table 5.2, which are discussed below. We can see the table 5.2. Melting and boiling points. The melting and boiling points of actinides are moderately high but are lower than those of transition elements. An inspection of the table 5.2 reveals that there is no regular trend in the melting and boiling points of the known actinides. Then have a look on the table 5.2, which tells us about the density, boiling point, melting point, radius of the metal ions of actinide series. Then the third point is density. An inspection of the table 5.2 reveals that the elements near uranium have very high densities. Americium resembles the corresponding lanthanide europium and being less dense than its neighbors. The fourth point is about ionic radii and actinide contraction. The size of the actinide ions decrease regularly along the actinide series. This is because with increasing atomic numbers, the extra charge on the nucleus is poorly screened by the f electrons. This steady decrease in ionic radii with the increase in atomic number is called actinide contraction. A comparison of metal 3 positive ionic radii of actinides with those of the lanthanide reveal the actinide and lanthanide ions are very similar in size. As a result, their chemical properties are also similar. The decrease in the ionic radii of metal 3 positive to metal 4 positive ions in case of actinides is shown in figure 5.2. Let's look figure 5.2, which is about atomic number and their radius of metallic actinides. It is interesting to note that there is a decrease in the atomic radii from thorium to uranium, which may be due to the increase in the most stable oxidation state from +4 to +6. In other words, the metallic bonding from thorium to uranium may be considered to consist of N positive ions with a total Ne electrons for atoms. After plutonium, the metal radius increases significantly again, which may reflect the increasing lanthanide-like behavior of the later actinides, in which the preferred oxidation state is +3 with only 3 electrons per atom available for metallic bonding. Let's discuss about the oxidation states. The actinides elements show a greater range of oxidation state than the lanthanides, particularly in each part of the series. The different oxidation states of actinide elements are shown in table 5.3. The +2 oxidation state in case of actinides is very rare. Americium 2 positive has the electron configuration 5f7. It is analog of europium 2 positive in the lanthanides but exists only in the solid state as the fluoride, americium fluoride. On the other hand, all the ions exist as ion in solution. The properties of divalent actinides resembles more closely to Ba2 positive in group 2. The most stable plus 2 oxidation state is exhibited by nobelium as nobelium plus 2 and corresponding to stable 5F14 arrangement. The plus 3 oxidation state is the most common oxidation state among all the actinides. However, this is not always the most stable oxidation state in the actinides. The first four elements, that is thorium, protactinium, uranium, and do not show plus 3 oxidation state as the most stable oxidation state. For example, uranium 3 positive is readily oxidized in air as well as in solution. Interestingly, the most stable oxidation state of elements up to uranium is the one involving all the valence electrons. Thus, the most stable oxidation states of all the elements are plus 4, plus 5 and plus 6 respectively. Although Neptunium shows the oxidation state plus 7 by involving all its valence electrons, it is not the most stable state. This is because Np is plus 7 oxidation state is highly oxidizing and the most stable state is plus 5. The plus 4 oxidation state is exhibited by all the elements from thorium to cerium. However, Pa and Np display the most important plus 4 oxidation state. The metal 4 positive ions are known in the acid solution and are precipitated by F negative, PO4 3 negative and IO3 negative. The elements all form dioxides and fluorides, tetrafluorides. The plus 5 oxidation state is exhibited by all the elements from Z91 to 95. However, plus 5 oxidation state is most stable for Pa and Np. It is important to note that metal 5 positive ions do not occur in solution as such. In fact, these states occur as their oxocation such as metal oxide positive ions. A few solid compounds are known whereas in solutions these ions disproportionate rapidly. The plus 6 oxidation state is exhibited by lower actinides in the form of their fluorides. The plus 6 oxidation state is more commonly found as the dioxo ions, that is metal oxide 2 negative. The metal oxide 2 negative is linear and exists both in the solid as well as in solution. One of the common encountered compounds of uranium is plus 6. Oxidation state is uranyl nitride dihydrate. It consists of linear ion surrounded by two NO3 negative ions and water molecules as shown. The NO3 negative groups are bidentate and therefore two oxygen from each NO3 negative are bonded to uranium. Oxygen atoms from the two water molecules also bond to uranium. Thus, the coordination number around uranium is 8. The uranium oxide 2 positive unit in the compound UO2NO3 whole twice, water whole twice, is perpendicular to a hexagon of 6 oxygen atoms, 4 from bidentate NO3 negative group and 2 from water molecules. The lower oxidation states are ionic, while the higher oxidation states are increasingly covalent. The plus 7 oxidation state is known only in the oxocations of Np and Pu when alkaline solutions are oxidized by O3. The important oxo anions known in case of Np and Pu are NPO4 OH whole twice 3 negative and PuO6 whole 3 negative. Color of the ions. Actinide ions are mostly colored. The color of the particular actinide ion depends upon the number of electrons present in the 5F subshell. The color of the actinide ion arises mainly due to FF transition. The color of the characteristic cations formed by the actinide ions in aqueous solution. In addition to FF transition in actinides, the color can also arise due to FD transition as well as charge transfer transitions. The color of the actinide ion solution because of FF transitions occur in the visible and ultraviolet regions. We have already encountered this F type of transition in case of lanthanides as well, since the 5F electrons in case of actinides are projected out more in space than the 4F electrons in lanthanides. These 5F electrons are strongly influenced by the ligand field of ligands. This makes the absorption spectra of the actinides more complex compared to the straightforward spectra of lanthanides. A complex spectra is always different to characterize easily. It has been experimentally found that the absorptions due to FF transitions in case of actinides are nearly 10 times stronger and 2 times broader than the FF transitions of lanthanide ions. The energy difference between 5F and 6D orbital in case of actinides being smaller than 4F and 5D orbitals in case of lanthanides. The actinide ions invariously absorb light of lower frequency. As a result, the allowed and very strong FD transitions lie in the ultraviolet region and therefore do not influence the color of the actinide ions. It has been observed that the actinide ions in higher oxidation state display predominantly charged transfer spectra. The spectra is exhibited only by high oxidation state ions which can easily oxidize the ligands. It is more important to note that lanthanides do not exhibit charge transfer spectra because lanthanide do not display oxidation state higher than 4. Here the colors of the metal ions of actinide series. Seventh point is magnetic properties. The actinides show similar magnetic properties to lanthanides in terms of magnetic moments with the number of unpaired electrons. This is shown clearly in figure 5.4, where the magnetic moments are plotted against the number of unpaired electrons. It is important to note that the high valence states have been chosen from 5F1, 5F2, 5F3 and 5F4 ions, which show the close similarities. Magnetic moment values for the isoelectronic actinide ions are lower than the lanthanide ions. This is due to the fact that 5F electrons in actinides are projected more in space to crystal field. As a result, the partial quenching of orbitals occur by the crystal field effects. Reactivity. The actinides are highly reactive metals. These react with dihydrogen and form non-stoichiometric hydrides with the formula MH2 or MH3. They react with hot water and tarnish in air, forming an oxide coating. The actinides react readily with HCl, but reactions with other acids is slower than expected. The metals are basic and do not react with sodium hydroxide. The actinides react directly with the halogens to form a variety of halides. The redox potential for known the M3 positive couples are about minus 1.9 volt. Thorium and uranium chemistry has been exploited in detail. Some of the general methods for preparing compounds of actinides are given below. Occurrence and isolation of actinides. All the elements beyond actinides in the periodic table are radioactive. As a result, the nuclei of all the actinides are unstable and undergo radioactive decay. Among the actinides, uranium is the heaviest metal naturally occurring element with an abundance of 2.4 ppm in Earth's crust. Among the actinides, thorium and uranium occur on the Earth. Uranium. Since uranium is the most important of all the actinides, the chemistry will be discussed in more detail. The primary natural source of uranium is pitch blende or uraninite, which has the empirical formula U3O8. It is a mixed oxide containing uranium both in +4 and +6 oxidation states. Extraction of uranium. As already mentioned, the main source of uranium is pitch blende. The details of the extraction of uranium involves the following step. First step is concentration. The ore is crushed to a fine powder and is subjected to convectional gravity separation to remove the lighter impurities. The second step is roasting. The concentrated ore is roasted on the hearth of a reverberatory furnace in the presence of air to remove the volatile impurities such as sulfur, arsenic, and antimony. Acid treatment. The roasting ore is treated with dilute H2SO4 in the presence of an oxidizing agent such as MnO2 or NaClO3. This treatment converts uranium to a soluble uranyl sulfate. The roasted ore can also be converted to a solution of uranium O2 NO3 whole twice by dissolving the ore in nitric acid. Treatment with ammonium carbonate. Addition of ammonium carbonate to the above solution of uranyl sulfate precipitate it as ammonium uranyl carbonate, which upon ignition gives U3O8. Alternatively, ammonia is used to the solution of uranyl sulfate obtained in step 3. This gives rise to bright yellow PPT of ammonium diuranate. The PPT is often called the yellow cake. This cake on heating gives rise to mixed oxide, uranium plus 4 and uranium plus 6 oxide. Conversion into uranium dioxide. The mixed uranium oxide U3O8 is reduced to UO2 by heating either with charcoal or with hydrogen. Production of uranium. Elements uranium can be produced from uranium dioxide by using either of the two methods. The first method is UO2 is heated with vapors of HF to form uranium 4 fluoride, which in turn reacts with magnesium to yield uranium metal. And the second method is by converting UO2 to a volatile uranium tetrachloride by heating it with elemental chlorine in the presence of charcoal. This is followed by the reduction with elemental sodium. All the steps detailed above can be summarized in the flow sheet diagram for the extraction of uranium. Chemistry of separation of neptunium, plutonium and americium from uranium. The three elements neptunium, plutonium and americium that follow uranium in the actinide series are produced mainly from uranium in the nuclear reactors. If you recall, uranium is the oldest known elements among the actinides. Naturally occurring uranium contains two main isotopes 238U92 and 235U92, which occurs in the ratio 99.3% and 0.7% respectively. There is another isotope of 233 uranium 92 which occurs in traces only. Neptunium and plutonium were prepared for the first time in 1940 by a team of celebrated scientists by bombarding uranium with neutrons in the cyclotron in Berkeley, USA. Both the elements are now obtained from spent uranium fuel elements of nuclear reactors when they are formed by the capture of neutrons produced in the fission. Isotopes of plutonium can also be prepared by reaction in which a fast neutron is added with the subsequent loss of two neutrons. Americium can be obtained from the isotopes of plutonium by the success reactions in the nuclear reactor, as the yields of the heavier elements after americium is controlled by two factors: the half-lives of the various isotopes and by their ability to absorb neutrons. It is important to note that the stepwise addition of slow neutrons is very difficult. A quick method is to bombard the nucleus with a large number of fast neutrons without allowing time for the intermediate product to decay. Separation of these elements, Neptune, plutonium, and americium from uranium, is extremely difficult and hazardous. It is because the elements, including the starting material, are not only highly radioactive but also give highly radioactive fission products. Plutonium, especially, is extremely toxic. A dose as small as 10 raised to power minus 6 gram may be fatal, while smaller doses are carcinogenic. The separation of neptunium, plutonium, and americium from uranium are based on the following chemistry. The first point is stability of oxidation state. A steady decrease in the stability of high oxidation states with the increase in atomic number have been observed with the increase in atomic number. The order of stabilities of the major ions involved are, whereas the order in case of the oxo ions are involved as separation of these elements from uranium from fission products and from one another can thus be achieved by adjusting the solution containing them to a suitable redox potential and then using solvent extraction or precipitation. Thus, plutonium can be removed by solvent extraction, whereas americium can be precipitated as AMF3 extraction into organic solvents. The metal oxide 2 positive ions from solutions can be extracted into inorganic solvents. The metal 4 positive ions are extracted into tributyl phosphate in kerosenes from 6-MnHNO3 solutions, whereas M3 negative ions are extracted from 10 to 16 M molar HNO3. Precipitation reactions. Actinides in plus 3 and plus 4 oxidation states can be precipitated as fluorides or phosphates from acid solutions. The higher oxidation states give either no PPT or can be prevented from precipitation by complex formation with sulfate ions. Ion exchange methods. Ion exchange methods are commonly used in separation for small amount of materials, as in the separation of americium. Spent uranium fuel rods removed from the nuclear reactors can be used to extract neptunium and plutonium in kilogram quantities, whereas americium in 100-gram quantities. The reprocessing of nuclear fuel rods is an important technology as this helps to extract new elements that may be used as nuclear fuel. Spent fuel rods are dipped in ponds of water for several days to allow them to cool. During this dipping period, the intensely radioactive isotopes with short half-lives such as 8.04 days lose most of their activity. The fuel rods are dissolved in 7 molar HNO3 and extracted with 30% tributyl phosphate in kerosene. The extraction coefficients of the actinides in 7 and HNO3 solution containing 30% tributyl phosphate in kerosene are as the metal 3 positive ions have very low extraction coefficients in 7NHNO3. As a result, nitrates of Pu4 positive are preferably extracted in tributyl phosphate, leaving the other actinides, namely neptunium and americium, along with the other fission products in aqueous solution. Thus, Pu4 positive is reduced to Pu3 positive, which enters the aqueous phase, remains unchanged in organic layer. On the other hand, aqueous solution of reduced plutonium 3 solution on treatment with nitrous acid gets oxidized to plutonium 4. This solution reacts with oxalic acid to give crystalline precipitates of the composition. Heating the hydrated compound to 300 degrees Celsius gives Pu dioxide. Plutonium dioxide. The whole sequence of steps outlined in the process are described below. The separation of other actinides, namely neptunium and americium, can be achieved by the use of appropriate oxidation reduction cycles coupled with solvent extraction. This is the table for uranium dioxides and uranium trioxides. Then the fifth point is transuranic elements. Elements with an atomic number greater than 92 are called transuranic elements. Before the Second World War, the elements that is thorium, protactinium, and uranium were located below hafnium, tantalum, and tungsten in the periodic table. The synthesis of neptunium, a new element with atomic number 93 by MC Mellon and Abelson in 1940, was demonstrated by bombarding uranium with neutrons. The newly discovered element should be positioned immediately to the right of tungsten below rhenium. However, the properties of neptunium resembled more with uranium rather than rhenium. It was the discovery of neptunium, followed by the subsequent synthesis of new elements, that were responsible for the new series of elements called the actinide series. All the transuranic elements are radioactive in the nature and have short half-life period. Neptunium, plutonium and americium were unknown prior to their synthetic preparation via nuclear reactions. However, these elements are later found to be present in trace quantities in uranium ores. Synthetic routes to transuranic elements. There are two synthetic routes which are commonly used for the synthesis of transuranic elements. A neutron may be captured by the nucleus with the emission of gamma rays reaction. The neutron increases the mass number of the nucleus by 1 unit, and some energy is released as gamma radiation. Further, neutron may be added in a similar way. Addition of neutrons increase the neutron to proton ratio. This makes the nucleus unstable because it contains too many neutrons. As a result, the nuclei decay by converting a neutron into a proton and a beta particle, that is an electron. This reduces the n by p ratio and also increases the atomic number by 1. Thus, a new element is formed. The other method involves the capture of small ions by the heavy nucleus. This is possible only if the bombarding particles have sufficient energy to overcome the Coulombic repulsions between the ion and the heavy nucleus. The smaller ions are accelerated in a linear accelerator or cyclotron to possess sufficient kinetic energy. The simplest ion used in the alpha particle. This increases the atomic mass unit by several units and the atomic number by 2 units. Synthesis of transuranic elements. All the transuranic elements have been prepared by nuclear reactions which involve bombardment with either the neutrons, alpha particles, or small other nuclei. Preparation of neptunium. It was prepared by MC Millan and Abelson in 1940 at Berkeley by bombarding 238 uranium 92 with slow neutrons when 239 92 uranium was obtained, and results in the formation of neptunium after the name of the planet Neptune. Preparation of plutonium. It was discovered by Seaborg and his co-workers during the beta decay of neptunium 239. Plutonium was named after the name of the planet Pluto. Preparation of americium. Americium was synthesized by bombarding 238-92 uranium with alpha particles. Preparation of curium. Curium was synthesized by bombarding 239-94 plutonium with alpha particles. Preparation of berkelium. Berkelium was synthesized by Seaborg and his co-workers by bombarding americium 241 with high-speed alpha particles. Preparation of californium. Californium was synthesized by bombarding curium-242 with alpha particles. Preparation of Einsteinium. Einsteinium was synthesized by bombarding U-238 nucleus with accelerated nitrogen nuclei. Two isotopes of californium have been identified. It can also be prepared by bombarding isotopes of californium-250 with neutrons. Californium-253 obtained during bombardment process results in beta decay forming Einsteinium. Preparation of fermium. Fermium was synthesized by bombarding Einsteinium with neutrons as preparation of mendelevium. Mendelevium was synthesized by bombarding Einstein 253 with alpha particles as preparation of nobelium. Nobelium was synthesized by the bombarding curium 246 with accelerated stripped carbon, that is carbon 6 positive. Preparation of lawrencium. Lawrencium was synthesized by bombarding californium 250 with accelerated boron nuclei. Here the table which shows the preparation of all the actinides. The later or heavier actinide elements. The elements from curium onward, namely curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium and lawrencium as named as later actinides. Very little is known about the chemistry of these later actinides because of their limited availability and extreme instability. It is clear from the table that curium is available only in microscopic quantities, whereas the later actinides above atomic number 100 have been prepared only in minute quantities. In other words, later actinides are available in tracer amounts. It is interesting to note that the later actinides show close resemblance to the lanthanides. However, the actinides can be easily separated from the lanthanides because the actinides readily form complexes. For example, the actinides react with concentrated HCl to form the corresponding chlorocomplexes. If both groups of ions are absorbed on the cation exchange column, the actinides can be eluted more conveniently with concentrated HCl. After eluting the actinides can be separated from each other by ion exchange using citrate solution to elute them. It is interesting to note that the order in which the tripositive actinide ions are eluted shows a close similarity to the order in which the tripositive lanthanide ions are eluted. Figure 5.7 displays the elution diagram for the actinides and the lanthanide elements. The first identification of the elements from americium to mendelevium on a weightage scale was made through elution. All the actinides with atomic number 96 to 103 with the exception of nobelium plus 3 as the most stable oxidation state. The most stable oxidation state of nobelium is plus 2. This is because it has the most favorable F14 electronic configuration. Actinides with atomic number 98 to 102 also display plus 2 oxidation state except for nobelium. Plus 2 oxidation state is strong reducing in nature. Higher oxidation state of curium plus 4 are found in the solid state in compounds such as CmF4. Similarly, berkelium compounds are stable in the plus 4 oxidation state such as berkelium dioxide. Lawrencium exists only in the plus 3 oxidation state and resists oxidation and reduction. This resistance to oxidation, that is plus 4, and reduction, that is plus 2, illustrates the stability of an 5F14 electronic configuration. The elements up to atomic number 100 undergo radioactive decay mainly by emitting alpha particles or beta particles. The later elements become increasingly unstable as the atomic number increases. Nobelium is extremely unstable and has a half-life of only 3 seconds. Elements beyond atomic number 103. The actinide series is complete at lawrencium 103. We have already learned that the half-lives of the later actinides beyond atomic number 100 decrease considerably. For example, the half-life of nobelium is only 3 seconds. It has been calculated that the half-life of the elements will decrease further as new elements are discovered. The half-life of an element with an atomic number 108 is expected to be very short, about 10 raised to power minus 4 to 10 raised to power minus 6 seconds due to spontaneous decay. As a result, it is extremely difficult to synthesize and study the chemistry of elements beyond 108. However, these difficulties have not dampened the spirit of the scientists, and they have been successful in discovering elements up to atomic number 112. Out of 112 elements, known elements up to atomic number 109 have so far been named. A major controversy came to light over naming these elements. The choice the choice is of the name of elements belongs to the discoverers. In the case of post-actinoids, three nuclear facilities are in competition for the synthesis of each of the now newly discovered elements. The facilities are at Berkeley, California, USA, Berkeley, Dubna, Russia, and Darmstadt, Germany. It is extremely difficult to identify which nuclear facility had the true claim. For example, the discovery of elements 104 was claimed by both Berkeley and Dubna groups. The Americans named the element Rutherfordium, while the Russians named it as Kurchatovium after Igor Kurchatov. While these conflicting claims were being settled, the International Union of Pure and Applied Chemistry devised a hybrid Latin Greek numerical system of providing provisional names and symbols to all the newly discovered elements. The name are derived directly from the atomic number using roots for the three digits in the atomic number of element and adding the ending ium. The roots for the number and their abbreviations are: for 0 nil, 1 un, 2 by, 3 tri, 4 quad, 5 pent, 6 hex, 7 sept, 8 oct, 9 int. In some cases, the names are shortened by removing the repetitive letters. Can be written as biome or triome. Let us name an element with atomic number 106 according to hybrid Latin Greek nomenclature. The name of the element is derived by combining together the roots in the order of digits, followed by adding em in the end. So the name of 106 will be un-nil-hexium. The symbol for the elements un-nil-hexium with atomic number 106 is UNH. Similarly, the name and symbol for the element with atomic number 102 can be worked out as un-nil-biome. The IUPAC name for the elements with atomic number more than 100 are given below. The newly recommended name for the elements with atomic number 104 to 109 are also mentioned. For 101, mendelevium, 102, nobelium, 103, lawrencium, 104, rutherfordium, 105, dubnium, 106, seaborgium, 107, borium, 108, hessium, 109, mithnarium. No IUPAC name has not been yet announced for 1102 to 114 atomic numbers elements. Comparison of actinides and lanthanides. Both lanthanides and actinides constitute elements of F block, as these involve the gradual filling of F orbitals. These elements occupy a distinct safe space at the bottom of the periodic table. They show close points of similarities and differences among the lanthanides and the actinides. Points of similarities. First point. Both the lanthanides and actinides involve the filling of f orbitals. Both the lanthanides and actinides display predominantly the plus 3 oxidation state in most of their compounds. Due to poor shielding of 4f and 5f electrons, both lanthanides and actinides shows gradual contraction in the size of their atoms with the increase in the atomic number known as lanthanide and actinide contraction respectively. Fourth point, the elements of lanthanides and actinides with the same number of unpaired electrons display similar absorption spectra due to FF transitions. Lanthanides and actinides are highly electropositive and are very reactive. Nitrates, sulfates, and perchlorate of trivalent lanthanides and actinides are soluble in water. Hydroxide fluorides are carbonates of trivalent lanthanides and actinides are insoluble in water. Eighth and the last point for the similarities of lanthanides and actinides that they can be separated by ion exchange method. Points of differences. The important points of differences between the lanthanides and actinides are presented in table below. Metal orbitals. Lanthanides, it involves filling of 4f orbitals. In case of actinides, it involves filling of 5f orbitals. Lanthanides, the energy gap between 4f and 5d orbitals in lanthanide is very large. As a result, their chemistry is fairly similar. In case of actinides, the energy gap between 5f, 6d and actinides is small. As a result, their chemistry is very different. In lanthanides, binding energy of 4f orbitals are higher in lanthanides. In actinides, binding energy of 5f orbitals are lower in actinides. In lanthanides, the most stable oxidation state is plus 3 in addition to some lanthanides showing plus 2 and plus 4. In actinides, the common oxidation state is plus 3 in addition to some actinides showing plus 2, plus 4, plus 5 and plus 6 oxidation states. In lanthanides, 4f electrons exert the greater shielding effect. Lanthanides in 5f electrons exert poor shielding effect. In lanthanides do not form oxocations where actinides form oxocation in higher oxidation state. Most of the lanthanide ions are colorless where most of the actinide ions are colored. The tendency to form complexes is small in case of lanthanides, whereas in case of actinides it is very large. All lanthanides except promethium are not radioactive, where all the actinides are radioactive. Lanthanides display coordination number 6, 7, 8 and 9. Actinides display higher coordination numbers, that is 8, 9 and 12. Compounds of lanthanides are basic in character. Compounds of actinides are more basic in character. So here our chapter ends, and the summary for review you can read that as the lanthanides and actinides constitute F block elements of the periodic table. The actinides differ from each other in the number of 5 F subshell and F electrons. The color of the actinide ions arise because of FF transition. The main source of uranium is pitch blende. Thorium has the highest melting and boiling point among actinides. Later actinides are elements beyond atomic number 96. Elements with higher atomic number than uranium are called transuranic elements. The 5f electrons of the actinides are far off from the positive charge on the nucleus compared with the 4f electrons of the lanthanides. The actinides use their 5f electrons in bonding and show a variety of positive oxidation states in their compounds. The actinides use their 5f electrons in bonding and show a variety of positive oxidation state in their compounds. Higher oxidation states are more prone to hydrolysis. Hydrolysis of higher oxidation state gives oxocations. A nuclear reaction where an atom captures a neutral followed by beta emission shows an increase in the atomic number by 1 unit. Fissionable material used in the nuclear reactors is called nuclear fuel.